So today we'll look at small signal models. We'll look at a couple of concepts before, and then look at the models for diodes and BJTs. So it's okay. So we perform the load line analysis for the common emitter amplifier, right? Where we are applying a DC biasing voltage, then we apply a small AC input signal and obtain the amplified output. Now, when we analyze these circuits, what we do is we apply the principle of superposition, superposition principle. And the great thing about this is we can treat the DC and the AC sources separately, so we can analyze the circuit separately. And again, the superposition principle allows us to analyze the circuit separately. And the way we can separate these out is by the addition of capacitors. So when we add capacitors in there, we are using, or we are applying the filtering property of capacitors. Okay, so we're using the capacitor as a filter. Now, here you can see there are three capacitors, C1, C2, and C3. All three of them have the same purpose. The functionality is the same. The result is slightly different. So capacitors at steady state at DC steady state, capacitor is going to behave like an open circuit, and it blocks DC signals, right? Capacitor behaves like an open circuit, and it blocks all the DC signals. Now, at the same time that it blocks DC signals, capacitor will behave like a short circuit and permits AC signals to pass through. Okay, permits AC signals to pass through. So if you look at C1 and C2, C1 is connected to the input, C2 is connected to the output. We apply DC voltages to set up the bias, meaning we set up the Q point, right? DC voltage is to set up the bias to set or to fix the Q point of the BJT. Now, if you have any unwanted DC signals appearing at the input, your Q point is going to shift away from its original value. And so we don't want that. And so we place a capacitor C1 at the input terminal to block any unwanted DC components to shift the Q point away from our desired value. And hence, C1 blocks unwanted DC signals. At the same time, we want our AC signal to go uninterrupted or unhindered into the base terminal. So we choose the value of the capacitor such that the reactance of the capacitor is very minimal for our desired frequency. So it permits AC input and value of C1 is such that reactance is negligible or is very low. Okay, is negligible or is very low. So C1 presents an open circuit to DC and a short circuit to AC. Make sense? Okay. Then if you look at the output side, C2, same thing. Now I'll ask you to think back to the lab output. When you perform the analysis, if you recall, the AC output signal was amplified to 10 volts peak to peak, but it had a large DC component or a large DC offset along with it. And that DC signal is unwanted at the output. And so we place another capacitor at the output to only permit the passage of our AC signal and blocks the DC component. So C2, again, we use the same functionality. It's filtering out the DC, blocking the DC, and it's allowing only the pure AC to pass through. So C2 is on the output side. Same application as C1. We want it to block the DC offset or DC component of the output signal and only permit the amplified AC signal to reach the output. As just an example, have you ever taken a small speaker and connected directly to a DC battery? Never ever? Where's your curiosity? I used to do it when I was a kid. If you have a very small speaker and you connect a DC battery, all you'll see like a whine coming out from the speaker. Constant whine. Okay. So as an example, if we do not have a coupling capacitor at the output and we connect this output directly to a speaker, let's say an audio application, we'd have the AC signal, I mean, we'd have whatever music or movie or whatever we are playing would be available at the output. But at the same time, we'd have the effect of the DC signal coming out as a low frequency whine. It'll just be like a buzzing noise through that speaker. And so we block that buzzing noise or buzzing sound by blocking the DC component and applying the capacitor. Okay, makes sense, right? So the input and the output side, the same thing. We have one more capacitor, C3, connected in parallel to R3 or R4, sorry, which is the emitter resistor. And the purpose for that, the functionality is the same. The purpose is different. Okay. C3 blocks the DC, but the application is that the Q point does not shift away. More importantly, it bypasses or it permits or it allows a pathway for AC signals to go directly to ground. Okay. It presents as an open circuit to DC, and it prevents the AC, unwanted AC signals from affecting our DC bias points. So it allows a pathway directly to ground from the emitter. So it does not affect our biasing circuit. Okay. And that's where the names of these capacitors come from the application. C1 and C2 are known as coupling capacitors because they couple the AC input directly into the BJT. And C3 is known as the bypass capacitor because it allows the AC signal to be bypassed. Okay. And that's the purpose of these capacitors in the circuit. So far, so good. Okay. All right. So let's split up. We'll look at the DC and the AC separately, right? The entire purpose of this was so we can analyze, we can simplify our analysis because we can separate out the DC voltages and the effects of the DC voltage sources and the AC input signal. DC analysis, you basically replace all capacitors and all inductors with their DC steady state equivalents. Okay, DC steady state equivalents. And for a capacitor, that means replacing everything with an open circuit. An inductor is replacing it with a short circuit. So capacitors replaced with an open circuit, inductors replaced with a short circuit. And because of that reason, the input AC voltage is no longer connected, and so is the output. And all we are left with in the circuit is a 4-resistor bias circuit or a voltage divider bias circuit. Okay, results in a voltage divider bias circuit. And that's it. Then we analyze it by applying KVL. You can find the voltages and the currents present in the circuit due to the applied DC voltages VCC and VEE if present. So that's one half of the analysis. Okay. For the AC analysis, it's the same thing, but now we replace it with the AC equivalents. So this all capacitors and inductors with their AC equivalents. And that means capacitors are short circuit and inductors are open circuit. Okay. Capacitors are short circuit, inductors are open circuit. Now, if you apply that principle to the circuit, the input voltage VI and R1 are directly coupled into the base. It is also connected to the output. And this is effectively removed because C3 is now a short circuit. So it's completely bypassing the emitter resistor. Also, if you look at the effect, what do we see? The effect of, actually, I jumped ahead. We also replace all voltage and current sources. So we replace all sources meaning a voltage source is replaced with a short circuit and a current source is replaced with an open circuit. And now look at the effect. Okay, voltage sources are replaced with a short circuit. Current sources are replaced with the open circuit. I would specify it is replace all DC sources. Okay, all DC sources. We are performing AC analysis, so we have to get rid of all the DC sources in the circuit. Make sense? So now let's look at the effect. What do we see? Because because the DC voltage source VCC is replaced with a short circuit, there is a direct pathway to ground. And that brings the collector resistor in parallel to the output resistor R3. Okay. And then at the same time, the base resistor R2 is also now in parallel with R1. So we are replacing the DC voltage source VCC with a short circuit that provides a direct pathway for RC and the top base resistor to ground, which brings it in parallel on the input side and the output side. And then you can further reduce it to one single resistance, output load resistor RL and base resistance RB. Make sense? This, of course, is just because it's a simple 4-resistor bias circuit. If it was a different circuit, different connections, different reductions. In this case, it just so happens that RC, the collector resistor, and the base resistor are on parallel in the input and the output side. And then at this point, we replace the BJT with its small signal model and analyze the circuit with VI or V in. Okay, small signal model. So then that begs the question, what is a small signal model and how small does the signal need to be? So stated last class, the reason we use small signal models for AC circuit is because we can apply, or not because, but it's so that we can apply all our techniques that we learned, our linear circuit analysis techniques. Okay, circuit analysis techniques for linear circuits or linear networks, and we can apply it to non-linear devices. So the signal must be small enough that when we look at a section of the characteristics, the signal looks linear, or at least has a linear relationship. And so then that's why we call it a small signal. So we look at a small signal model of a diode first, and then the small signal model for a BJT, and we also see what needs to be, what the value needs to be in order to be considered a small signal. So for a diode, if we apply DC, voltages and set the bias point, we have value for VD and ID, right? That's our set Q point from the DC bias voltage. Okay, DC biasing voltage. Then when we apply an AC signal on top, VD and ID are small shifts in the values of VD and ID due to the applied AC signal. Again, repeating the use of the word small. Okay. So there are small shifts away from the Q point due to the applied AC signal. So let's apply Ohm's law. What do we get? RD is simply the ratio of VD over ID. VD over ID. That's the diode resistance RD. Again, we are treating it as linear. So it's a very small section right around the Q point. And because it's small enough, we can treat it as linear. If it's linear, then we can apply Ohm's law to it. And we can define the relationship between the diode voltage and the diode current as the diode resistance RD. And so we can model the diode as a resistor RD with voltage VD and current ID flowing through it. And so the small signal model of a diode is simply a resistor with the value RD. Let's take a pause, think over that. Let me know if you have any questions. Does that make sense? Our diode is a nonlinear device. Okay, if you look at the entire characteristic, it's nonlinear. Current does not have a linear relationship with the voltage. But if we zoom in so far that we have a very small slice of the characteristic, we can treat it as linear. And within that small slice or small piece, the current has a linear relationship with the diode, with the voltage. And so ID versus VD is linear. And if it's linear, we can apply Ohm's law and we can define the relationship between the current and the voltage by the diode resistance RD. And so any small shift due to an applied AC signal, if it's small enough, we can define it as the diode resistance RD, which is VD over ID. And from there, we can define the reciprocal of the diode resistance as the conductance GD. Okay, conductance GD. Conductance GD is ID over VD. Okay. Now, if we want to solve this for a forward bias diode, we simply plug in the diode equation in here, and we can obtain a value for GD. Okay, so for a forward bias diode, GD is equal to ID plus IS over the thermal voltage VT. And because in forward bias, ID is likely to be far more than the saturation current IS, you can approximately write this as ID over VT. Okay, so how small does the signal need to be in order to be considered, in order to be applied small signal model? And we derive that and we can obtain VD must be far less than twice the thermal voltage. Common voltage at room temperature is about 25.8 millivolts, or as our book uses, 25 millivolts. So we can write that the shift must be far, far less than 50 millivolts. An accepted value is a ratio of 10. So VD must be less than 5 millivolts in order to be considered small. Okay, to be considered small. And that is the diode small signal model. So then let's look at the BJT small signal model. And to do that, we will begin with a two-port network. And this is not the hybrid pi. I need to change that. Okay. We are starting with the Y parameter. Two-port model. And you can see we can split up so BJT, of course, unlike the diode, has two ports. And so we can write the left side is the input port, right side is the output port. Emitter, of course, being common between the two. On the input side, we have the base, we have the base, and the output side, we have the collector. So the input side is a combination of the base current IB versus the base voltage VB. Output side is the collector current IC and the collector voltage VCE. So the two equations we can write are for IB and IC. And IB would be the sum of VBE and VCE. And then related by the conductance parameters. So let's write it out first. And IC would be, again, VE and VCE. So these conductance parameters are what? Okay. So they are G pi, G mu, Gm, and Go. Go. Okay. And they are dependent current sources on both sides. So if we are analyzing these at the Q point and we wish to find the values, then VCE would be 0 and VBE would be 0 in turn. So we can describe G pi if VCE is equal to 0, then we can describe G pi as IB over VBE. And you can see it's only the input current and the input voltage. GM, transconductance, IC or VBE. G pi is, of course, the input conductance because it's only the ratio of input current and input voltage. GM is output current as a function of the input voltage. How is the input being transferred to the output? Hence, transconductance. And then if VBE is equal to 0, then G mu is IB over VCE, and GO is IC over VCE. Okay. Now at the Q point, we can write G pi sorry, not G pi, G mu is equal to 0. Gm is IC over VT. GO is IC VA plus VCE. And then G pi requires the definition of a new term. IC over beta O times VT. And beta O can be written as beta F, and then 1 minus IC times 1 over beta F, partial derivative beta F to IC at the Q point. Slope of the curve, function of the forward beta gain is IC. Now remember, there's a slope in the output characteristic curves. As the IC increases, the beta also increases. So the slope of that line, we can use that to describe beta O. Now, the reason it's called kind of like a pi model is because early on someone saw the similarity between the structure of the model, the physical structure of the model or description of the model, and the Greek letter pi. Okay, so conductance subscript pi is on the input side. It's showing you the input conductance. If you take the inverse, it gives you R pi, which is the input resistance. GO is the output conductance. If we take the reciprocal, we get RO, which is the output resistance. So it describes both the input side and the output side. And both input resistance and output resistance are a key factor when you're trying to design an amplifier circuit. Okay. From this, we can refine this model and we can obtain a very popular model known as the hybrid pi model. Hybrid pi model. And the hybrid pi model, again, as I was saying, you have the input resistance R pi, output resistance RO. The currents, if you will, take notice, are both entering into the transistor. It's not flowing out. They are both flowing into the transistor. So sign convention, of course, is that IB is coming in, IC is coming in. And then, of course, they both form the emitter current IE. Right? IC plus IB is IE. So in the hybrid pi model, the value for GM is simply IC over thermal voltage VT. That is our transconductance. How is the input being transferred to the output? A very important parameter. We have the input resistance R pi. That is beta O times VT over IC. And then output resistance RO is 1 over GO. And that comes out to be VA plus VCE or IC. And because the early voltage is usually large enough that we can ignore VCE, we can write the output resistance is approximately equal to VA over IC. And that's the output resistance. So you can see how the early voltage has an effect on the design of an amplifier due to output resistance. Okay. These are all the equations that you need to solve for the homework. In case you have not yet seen the announcement, there's a homework due next week. I was going to make it due Monday night, but then I decided to extend it till Tuesday night. But didn't want to intrude on the Thanksgiving weekend. So get done with the homework. I will be available all through the weekend and all through the break via email and if Zoom if needed. We'll have a quiz the week after, meaning the Monday that we get back. Okay, that'll be our last and final quiz before the final exam. The final exam page will be updated with a survey at the end. You have the option for Saturday as well as the regular Monday and Wednesday schedule. That page has been online since the beginning of the quarter. So again, I will update with some other details that are needed. But other than that, we'll end class here today. And then the one final thing remaining is we'll look at an example in the last week, with regards to small signal model. All right. Have a happy Thanksgiving break, and I will see you next month.